Okay, Arkadaşlar, time to get back to cache memories. All right, where we left off was a quantitative analysis about cache performance. And we saw that with faster and faster processors, caches are desperately necessary, but even the hit rates, 96, 98%, still cause us to stall quite a lot. So that's a big challenge to computer architects as to how to make up for the enormous gap between processor performance and memory performance. We'll get back to that later as we talk more about multi-cores. This next slide talks about average memory access time and basically gives a formula and asks a little problem. But before we do that, I'd like to look at the top part. What about making cache bigger? Wouldn't that be a great idea, Hoja? Bigger caches will have smaller miss rates and higher hit rates. Sounds like a tempting idea, but we know that bigger caches will also have bigger hit times. So if you want to slow down the instruction cache and slow down the memory cache, make them bigger. All right, so what's that going to do? Well, it's going to cause our clock cycle time to be stretched by the fact that we have to go to instruction cache to fetch in our pipeline, and we have to go to data cache to write or read in our pipeline. Well, one solution would be don't stretch the clock cycle, make them multi-cycle accesses. Remember, we had some pipelines where it takes more than one cycle to fetch, it takes more than one cycle to access data memory. I think I showed some on the board in an earlier slide. So we could make cache access multi-cycle. That would keep the clock cycle fast and just say use 2, use 3, use 4 on these big slow caches. Can anybody see any disadvantage of that? So I've got a 5-stage pipeline, but because the caches got too big, they got too slow, so it became a 7-stage pipeline. 2 for fetching, 1 for decoding, 1 for ALU execution, 2 for data memory, and 1 for write back. So it became a 7-stage pipeline instead of a 5-stage pipeline because I have these bigger, slower caches that I have to go to. What would that do to my overall system performance? Clock is still just as fast. Pipeline's deeper now by 2 stages. What's going to happen? Nothing. Okay, great. Let's make, instead of 7-stage pipe, how about if I go to 17-stage pipe? Any performance problem with 17-stage pipeline? I still turn out 1 instruction per clock cycle, don't I? Oh, how about 37-stage pipeline? That sounds even better. Is there any problem with deeper pipelines? Cost of what? Oh, no. Transistors are cheap. No. We got 1 billion of them. No. What happens when pipelines are deeper? Yeah, of course I have more, but he said, more cost, and I'm saying, no, it doesn't matter. Transistors are cheap. Is there a performance problem with deeper pipelines?
So we have same stages, but...
No, we have more stages now. More stages. Not same, more.
But they're, again, I guess same to our operations.
Yeah, the operations are still the same operations. Yeah, we just made the pipeline deeper. We didn't change the ISA, but we changed the implementation of it. Can anybody tell me if that's going to cause any difficulties? Oh, now we're talking about when all doesn't go well and I have a problem, like I have to flush or stall or try to forward, or an exception happens, or I try to predict on a branch and I mispredict. What happens in all those cases for deeper pipelines? Yeah, the price is worse for anything going wrong. So in fact, deeper pipelines don't perform as well as shallow pipelines if they have the same clock rate, because whenever anything goes wrong, you get hit worse. You lose more instructions when you have to flush. You stall longer in order to recover. Forwarding may not always work as well for deep pipelines as short pipelines. So if you can't forward, you have to stall. Yeah. So adding stages to the pipeline will cost you in performance. It's not easy to measure. You'd have to run simulation studies. But it's very clear. If all goes well, no problem. But if all doesn't go well, and we can think of some cases, load use hazard, branches, exceptions, all those kind of things, when all doesn't go well, deeper pipelines are clearly worse than shorter pipelines. So therefore, at some point, the increase in the hit time for a larger cache is going to cause us to probably have to add extra stages to the pipe for those slow memories, and that's going to overcome the improvement in hit rate on memory because it's going to cause a decrease in processor performance. So at some point, you say, oops, now I was trying to help and I actually overall hurt. So making bigger caches has some limits to it. All right, now let's look at the formula. The formula says the average memory access time is how long it takes for a hit, plus when you don't hit, some percentage of the time you have a miss penalty, or the miss time. So hit time and miss time both are part of the average memory access. Let's do a little quick calculation. See if you can do this with your partner by yourself there. The numbers are given at the bottom of the slide. So why don't you just talk about it or write it down and work it out, okay? This problem right here at the bottom of the slide. Okay. Take a couple minutes and just go ahead and do that problem there at the bottom of the slide. What's 2% of 50? 1. So one cycle when you hit, but a cycle on average for missing. So the grand total is 2 cycles. So therefore 20 picoseconds plus 20 picoseconds. Grand total is equal to 40 picoseconds. Now here's what I want you to see from that simple little math is a nice fast memory access is slowed way down by a 2% miss rate. I mean, that's pretty good. That's 98% hit rate, 2% miss rate. But what you thought was 20 picosecond access time is now actually 40 picosecond access time on average. Everybody see this? Because this is so big, even this being tiny and little still makes this factor an important part of the whole thing. Keshke, this was so small. Wouldn't it be lovely if the average was 22 or 23? But it isn't. It's 40. All right. Again, one more time. I'm trying to show you by Charpaja examples here the extreme price that we're paying for cache misses. The extreme price we're paying for cache. Your memory behaves like it's twice as slow. Now, if you're at all familiar with memory, you know that you pay according to the access time. So if you want fast memory, you really pay extra money for it. If you've bought any memory lately, you know that they'll talk about memory access times. So the more you pay, the faster it's supposed to be. So let's say you paid some really good bucks and you got 20 picosecond access time. Oh man, my chips are hot. This is great, latest and greatest. And now you find out that it's going to behave like 40, the cheap stuff, because of a 2% cache miss rate. That's what I'm trying to show here is your money is going down the drain. You'll be flushing it down the toilet. Okay, you paid the bucks for the good fast memory. You didn't get the performance of the good fast memory because of miss rates. Okay, now let's talk about how to reduce miss rates. I hope I've motivated enough that cache miss rates are a big, big deal. You know, 98 and 99% seem like a really small difference to you and me, but you can tell it would make a huge difference here, wouldn't it? Okay. What would it do to that one if I had a 99% hit rate? It would reduce this miss rate to 1 here, wouldn't it? And so what would that do here? And so what would that do here? Wow. It got a lot faster just by 1% decrease in the miss rate. Are we interested in decreasing the miss rate now? I hope so. Let's do it. Okay. One way to do it is to allow more flexible block placement. to reduce the amount of conflict misses. In a direct map cache, as we know, a memory block maps to exactly and only one place in the cache that it can be. And at the other extreme, we could have thought of a cache system that allows any memory block when it's in cache to be anywhere. That's the extreme flexible option. This is the extreme restrictive option. You can only be in one place. You're not allowed to move to the left or the right. This one says, hey, any room in our hotel is fine. This one says, we've got a reserved room for you, but it has to be that one. We're sorry, sir, sometimes it's full with somebody else. Can't I stay in any other room? No, that's your only room. It has to be that room, or you don't stay at our hotel. This one says, hey, any room is fine. Most hotels prefer this policy so they don't have to turn away customers. Okay, that's a good life example. Now, a compromise would be to be between these two extremes. This is one extreme, that's the other extreme. And we call this a fully associative cache. And we call this kind, the compromise, a n-way set-associative cache. Notice the word associative here. Though this is one-way associative, this is fully associative, this is n-way associative, where n is bigger than 1, but not as large as the fully associative. The idea here is that we have a set of locations. In fact, the number of them is n, and any of those n locations can be where the memory block will be mapped. That would be like a hotel that says, sir, we're glad you're here. There's 4 rooms that we can put you in. And since 3 of them are full, we'll put you in the other one. Or any of them, they're all open, we'll put you in, but none of the other rooms are for you. So we have a set now, bigger than 1, that you can stay in, but not as big as our whole hotel. Okay, got it? This is, you have only 1 room that you'll ever be able to stay in. You can stay in anywhere in the whole hotel. That you have n rooms that you can stay in. That's the analogy I'd like you to think, okay? So to figure out where you stay in this approach, we use the same idea as we had before. The block address is modulo, but notice it's not number of blocks in cache, it's number of sets. And a set is the group of rooms or group of blocks that we link together in what's called a way. There are n ways in an n-way cache. You'll see a picture of it real quick right here. Okay? Look at this. The index says that if it's found in this cache, it'll be found here, or here, or here, or here. This is called a 4-way associative cache. And I can put what I'm storing that matches this index that has those bits in this one, or this one, or that one, or that one. So if these 3 are full, I still have a place to put it. It can go in any of those. If they're all 4 full, then I'll have to kick out somebody in order to put it in. But I'm not allowed to put it here or here, but I do have 4 different locations that I map to. It's 4-way set associative. Now let's go back now and see what happens if I don't have. In a direct map cache, what do you expect is going to happen when my string of memory references is 04, 04, 04, 04? What do you think is going to happen? Yep. There's my 0. There's my 4. I've got 4 blocks in the cache, so everybody can see that the index bits are 00, 01, 10, and 11. Unfortunately, these both map to the same index. Their tags are going to be different, so you know what's going to happen. The first reference to 0 is going to be a miss, and we'll put it here with tag 0. The second reference to 4 is going to be a miss, and we'll put it here with tag 01. In other words, 01 is the tag that goes here, and the data from 4 goes there. Then we reference 0 again, says you get out, I have to be there. Reference 4, you get out, I have to be there. We get 8 misses in 8 references. There's no sharing possible. It's one-way set associative. There's only one location that 0 can be in, only one location that 4 can be in, and Malisev, it's the same location. Full conflict misses. 2 cold start misses followed by 6 conflict misses. 0% hit, 100% miss in this situation. All right? Now, obviously, the problem is caused by this ping-ponging back and forth, 04, 04. We could solve this, couldn't we, if we had 2 different rooms, and we said to Mr. Customer 0, well, we've got 2 rooms, we're going to put you in this one, and then Customer 4, there's only 2 rooms you can stay in, and one of them's full, but the other one's empty. We'll put you in that one. And that's what's going to happen. We're going to reduce the conflict misses. Watch this. Okay, you can see that we put Customer 0 in this location. Oh, first I have to define the architecture, sorry. Let's go back here. Okay, what I've got here is only 2 sets now. It's still 4 locations in the cache, but 2 sets, set 0 and set 1. What are sets? They consist of 2 different members. the member in way 0 and the member in way 1. So this set, 0, consists of two different locations, both of which are matched to on the same index. Now, since I only have two sets, okay, I now look at only this for my index. So I've got two possibilities. I'm either going to map into set 0, which is here, or set 1, which is here. But I've got two locations in each one that I could put them in. So you can see here that this will map into set 0, this will map into set 1, this will also map into set 0, this will also map into set 1, this will also map into set 0. We'll look at that. There's my memory address 4, which maps to set 0, and there's my memory address 0, which also maps to set 0. Is there going to be a Chakishma? And the answer is no, if set 0 contains more than one block, or more than one way, or more than one member. Does set 0 contain more than one member? Yes, it does. It's got two ways. So we'll be able to fit them in. And as you would expect, here's what it looks like. 0 comes in and goes to this location. Then 4 comes in and it has to go to this location. That one's full, but we've got a parallel location. The tags are different, but the set number is still set 0. And after those two cold start misses, we go hit, 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 hit. We have a hit rate of 75%, the best we could imagine getting. Two cold start misses followed by 6 hits. Okay, got it? So we solved the conflict miss problem with set-associative caches. Okay, 8 requests, only 2 are misses. Those are the compulsories. Okay, so what do? We solve the ping-pong effect due to conflict misses, since now two different memory locations don't map to the same exact location. They can coexist in a set of size 2. Now here's a 4-way set-associative cache with the architecture that we need to see. Can everybody notice that what's going to go on here is I'm going to take the index, and the index is going to say, look at this set, and in parallel ask the question of all 4 ways, do you have the one which matches the tag I'm looking for? So here's the tag we're looking for, and that question is asked here, and here, and here, and here at the same time. So to ask the same question in hardware 4 different ways at the same time means you have to have 4 different comparators. So I've quadrupled the amount of hardware to do that 4-way test in parallel. And I certainly wouldn't want to do it artificially to ask one, oh, it's not you, go to the next door, hello, or is it you? No, that will be too slow. I'm looking for a fast access time on a hit here. So I ask the question, do the tags match? And then I also ask the question, is the valid bit set? And you can see I'm going to get an answer from here, and an answer from here, and an answer from here, and an answer from here. And those 4 answers are going to be either all say no, or 3 say no and 1 says yes. I can never have 2 saying yes at the same time. Why? Why can I never have 2 saying yes at the same time? Because that would mean that I've got the same tag here and here, which means I stored the same thing twice in 2 different locations. I won't do that. Okay. So therefore, I'm going to, on this OR gate, either have all 4 low, or 1 high, and the other 3 low. So my answer here is going to be, if one of these is 1, I get a hit. If they're all 0, I get a miss. Clear as can be. So I get my hit after comparison and ORing the signals together. Now, if I have a hit, which one is it? I have to select that in a 4-to-1 selector. So you can see here that those signals also need to be somehow combined in order to tell this 4-to-1 mux which one to take, because it has 4 inputs, and it's going to pick one if it's a hit for my data. See the architecture about that? That's how it works. Now, what did we see before? What we saw before was just this much, that much with 1 comparator and the selector, right? We didn't have this OR gate. We had a single hit signal, which came from right here. Remember? Okay. And we didn't have this unless we were choosing among multi-word blocks. Okay, the only thing left to talk about is how the address is sent here. Obviously, I've got some index bits and some decode bits. Some tag bits. How many index bits do I have? How many index bits do I have? No, I mean I have 8, but why do I have 8? How many? What determines the number of index bits? Yeah, this. That determines it. If it's 512, then I've got 9. If it's 32, then I got 5. It depends on how many of those do you have. Now, what determines that? What determines that? Yeah, cache size. But notice this isn't the only thing that relates to cache size. The other thing is that. Yeah, exactly. I've now got a two-dimensional cache. I've got number of ways in a set, and I've got number of sets. With me? Okay. So if I therefore increase this, my cache got bigger unless I decrease this. If I increase this, my cache got bigger unless I decrease this. With me? Now, what do we know about bigger caches? Slower. And what else? Higher hit rates, lower miss rates. One good thing, one bad thing. Okay? Now, this is not about bigger cache. This is about how to spend the size of the cache in a particular way, namely with associativity. Do you see the associativity here? I could just get rid of these and make this 4 times as long. But instead, what's been done, remember we had 1,024. I've reduced the number of index bits to 8 instead of 10 and given myself 4-way associativity. Same size, different organization. The question is, does that help or hurt my hit rate? Would it be better to have 1,024 cache blocks, each of which is just one-way set associative, or is it better to have 255 sets? Each set contains 4 cache blocks, and I have, what do you think? What do you think? This is better. We reduce the conflict misses. I'm going to show you some numbers about how much in just a minute. Let me see if I've got this. Yeah, okay, here we go. For a fixed size cache that says, x sharp of y is some fixed number, spending your transistors, each increase by a factor of 2 in associativity, from 1 to 2, from 2 to 4, from 4 to 8, doubles the number of blocks per set. Yeah, that's right, sure. Doubles the number of blocks per set. So if you fix the size, that shrinks the number of sets. We just get wider. X gets bigger, Y gets smaller. And halves the number of sets. It decreases the size of the index by 1 bit and increases the size of the tag by 1 bit every time you do a factor of 2. Right, that makes sense. Let's go back one. There's this boundary right here is moving according to how many members of the set I have and what the number of sets is. Okay, fine. So that means that if we think about this, this right here is the boundary. If I increase my associativity, I have less sets, so my index bits need to be less, and my tag bits will need to be more. If I go this way all the way to there, I have a fully associative cache. Right? I mean, anything can be anywhere. I have one set, and it's enormous with all the members, meaning be anywhere you want. No need to have an index at all. If I go this way as far as I can, then I've got the direct map cache with only one way, smallest size tag, biggest number of index bits because I have the most number of things in the cache. There's only one way. Okay? Now, all the time, I still have to have block offset. If I have multi-word blocks, then I've got which word in the block, and I've also, of course, got a byte offset. The last 2 bits are always a byte offset because these are 32-bit words, and my addresses are ultimately byte addresses. Okay, now, the cost and the benefit of an associative cache. What does it cost us? What does it benefit us? Is it worth doing? When a miss occurs, which way's block do we pick for replacement? It's a good question. When a hit occurs, that's easy. I show it how to find a hit. But what if there's a miss? Time to kick somebody out. Well, one approach very widely used is least recently used. Kick out the oldest one. Why? Why kick out the oldest one? Cause?
The data that we use probably will be used later.
The data that we used recently, we will most probably use again soon. Who says that besides Ur Kumru? Yeah, temporal locality, right. It's not about neighbors, it's about come back again soon. What do they sell you at a store when you shop? Thanks so much. Bekliorezine, right? Come again soon. What do they tell you when you go visit somebody? Bekliorez, come back again soon, right? If you've been there, they hope you're going to come back again. Right? This is the same thing here, temporal locality. All right, now, in order to do that, the one that's been unused for the longest time, you have to keep track of which one it was. So you need to have some hardware, some extra bits to know when you accessed and who's the oldest one, etc. If you have two-way set associative, you just need a single bit. The single bit says which one's the old one, which one's the new one. Every time you access one and put something in or read from it, you make it the new one and you make the other one the old one, right? So if you access the new one, it stays new. If you access the old one, then the bits flip. That's easy, a single bit. If you had 4, it'd be a little more complicated with 2 bits to know who's the oldest, second oldest, newest and second newest. All right, now for n-way set-associative caches, besides this cost of having to know who to kick out, you got to have n comparators. I showed you there were 4 comparators on that 4-way, and the comparator, of course, adds delay, and it adds some area. Area we're not so worried about, but delay means you got to go through the comparators in order to get the result. There's a mux now. We had to have a big 4-to-1 mux in that case, and the mux is going to slow down the time to select which one and get it out, right? So before the data is available, it's got to make it through a mux. I just added additional delay, so the hit time got slower. The data is available after you select the set and the hit-miss decision. In direct map cache, the cache block is available before the hit-miss decision. I have data, maybe it's good, maybe it's bad, but I already have it. Here, I have to decide if I had a hit before I can even let the mux choose which one. So that's not so good. So it's not possible to just assume a hit and continue on and then record later if it was a miss. We can't go ahead and then roll back and say, oops, it was a miss. Now we're forced to wait. So it slows the cache access time, the hit time down. All right, all those disadvantages, do we have any advantages? Yes. What's this? Miss rate. What happens? It's going down. How is it going down? Oh, increase the associativity, and the miss rate goes down, but not forever. Wouldn't it be nice if it just kept doing that? But it doesn't. Notice what happens. It kind of flattens out here. So you can see that going from 1-way, which is direct mapped, to 2-way set associativity brings quite a benefit. Not so much for these guys, which are the larger size caches, but especially for the smaller size caches, you get a big benefit. Then going from 2-way to 4-way brings a little more benefit, but not near as much as the first one. Going from 4 to 8-way hardly brings any benefit at all. But you know, if it brought a change of 10% or even 5%, might be worth it. If it brought a change of 2%, you might consider it. It's just a rearrangement in the cache with a little extra, as we said, area for the extra costs of the comparators. Are we trying to lower miss rate? Does this lower miss rate? Yes, it does. Dramatically, and then less dramatically, and then less dramatically. Notice the biggest effect is seen in small caches, not so much in big caches. Can anybody answer why? Why does a big cache not benefit so much from the associativity? We have a lot of space anyway, so the conflict misses are going to be not so yown. Remember, n to 1, it's a smaller n if I have a bigger cache. Yeah, exactly. Yeah, exactly. So in a way, I made extra spaces for 0 and 4 to not have conflicts. But still, there will be some. So this will help even these, but you can't see it very well in this graph. Okay, so here's the bottom line. The largest gain is going from direct map to 2-way. You get about a 20% reduction. Look, from 10 down to 8, or from 7 down to 5.5, all right, or whatever the percentages are. Now these are miss rates, so look, 10% miss rate means 90% hit rate. What are we at down here? 1% miss rate means 99% hit rate. So what have we got over here? I don't know, 98.8. You know, it didn't go down very much, but it went down a little bit. That's the point I wanted you to see on this graph. There's lots more graphs in the book. Please read chapter 5 and look at this kind of data. Okay. Now the second way to reduce the miss rate is to use multiple levels of cache. So one way is to reorganize the cache that you have, or make it bigger and make it set associative both if you could spend the transistors, but that slows it down. And then the other way is to have multiple levels of cache. I think all of us are aware that L1, L2, even L3 cache is pretty common these days, right? Multi-level caching. Let's see how that might benefit us. With advancing technology, we've got lots of transistors. We have more than enough to make bigger L1 caches or to put a second level of cache on, a level 2 cache, or even level 3. We'll see that in just a minute. Now, normally level 2 cache is unified. So level 1 cache has got a data and an instruction cache which are different from each other, because data is going to be read and written to in the data cache, instruction cache is just for the code. But at level 2, it's normally a unified cache. So it's just one cache for level 2 things. Both code and data would go in there. In some cases, even a unified level 3 cache. We'll see that in just a minute on a future slide. So let's now run our example again. Remember the example we did? The ideal CPI was 2.0. When we missed, we had a 100-cycle miss penalty to go to main memory, and we had a 36% loads and stores and 100% fetches, and we had these penalties of 2% or 4% for the instruction and data cache. Let's say that we now put in a extra cache in between level 1 and main memory. So we stick in a level 2 cache, and it's unified, so that's why it says UL2. And let's say that it has a 0.5% miss rate. Now watch what happens. The level 1 caches have miss rates that are 2 and 4 because they're small. This is going to be a lot bigger, so it's going to have a lot smaller miss rate. Let's also say that the miss penalty now for level 1 is 25 cycles instead of 100. In other words, if you miss in level 1, you don't have to go to main memory. You just go to level 2. And it's a cache, so it won't cost you so bad. Yeah, if you miss in level 2, you have to go to main memory. So the architecture looks like this now. We've got CPU looking for level 1 hits. If we don't get a level 1 hit, we look for a level 2. If we don't get a level 2, we go for main memory. And if you remember before, without this, we said this is 100 cycle, but this is going to be smaller than this and faster and made out of static RAM technology, let's say. So it's only 25 cycle. Yeah, it's off the chip, it's slower, but the idea of sticking this in and making it big enough is that even if the miss penalties here are 2% and 4%, the miss penalty here is only 0.5%. All right, now you can see that 0.5% of the time I have to pay the 100 cycle penalty. But what I want you to see is 2 and 4% of the time I don't pay the 100 cycle penalty. By sticking this in, I only pay a 25 cycle penalty. Ah, so that's going to help us a lot, isn't it? Should help us quite a bit because the same percentage of the time I miss in level 1, but I don't pay 100 cycle. I only pay 25. And when do I pay the 100? Only 0.5% of the time, okay, instead of 2 and 4. So if you run the math again, here's what it looks like. The CPI with stalls is the ideal CPI plus 2% of the time you miss in instruction cache and you have to pay 25 cycle penalty to go to level 2. And 36% of the time you have a load store instruction, and 4% of those you miss in level 1, you have to go to level 2 and pay a 25 cycle penalty. All right, so that's the same as before, except we substituted the 25 instead of the 100. So it's, of course, going to be better. But there's a little more to the story. 0.5% of the time, you miss in level 2, and you have to pay the 100 cycle penalty on instructions. And 36% of the time, 0.5% of that, you miss in level 2 for data and have to pay 100 cycle penalty. Okay? So those 5 things added together equals 3.54. And before it was 5.44. We saved almost 2 clock cycles. Huge improvement because of this. In other words, you might say that the penalty went from 3.44, in other words, 2 plus 3.44, it now went to 1.54. We cut the penalty in less than half by doing this. And we still have 2 cycles for the actual CPI, but the extra was 3.44, now it's 1.54. Got that? Yeah, our penalty for memory stalls is cut in half by doing this. Why isn't it cut in a fourth by doing this? Look, 100 in year and day 25, 100 in year and day 25. How come it doesn't go to 1/4? The answer is because there's a little bit more to the equation here. It doesn't stop right here. This doesn't have a 100% hit rate. You can miss there and go to here. And even though that's a tiny percentage, 100 cycles hurts bad. It hurts a lot more than 25 cycles. Okay. That's another mathematical example, and obviously I'm not just saying this so that it's interesting, isn't that nice, Hoja can multiply. I'm saying this so that you can see solved examples of problems done with math in order to be able to calculate miss penalties, memory performances, effective CPI with memory stalls. This is for you, it's not for me, it's for you. Okay, questions? Yeah. What do you mean writing?
You have to write more than one level.
No, do you remember what we said? We said traffic between here and here doesn't exist. We said each level only talks to the level below it. So there's traffic this way between those. There's traffic this way between those. There's no traffic like that. That doesn't exist. So that if you miss in level 1, you tell level 2 I need it. Level 2 gets it and gives it to you. So there's your traffic. If level 2 has it, it gives it to you. If level 2 doesn't have it, then level 2 says, I missed, I need it from you, main memory, and gets it and puts it there. Or main memory misses and it asks for it from disk. So each of these are independent things. That's why it's fair to say, when I miss here, it's 25 cycles to do business with here. When I miss here, it's 100 cycles to do business with here.
By writing, now you need to change anything. You have to change it all for them.
If you do write through. But the other alternative, which we talked about, is write back. And remember, write back means write back later, and write through means write through now. That's the key difference, later versus now.
Much more thing to write if multiple rows, then there's a little bit stall time that writes up a little bit more frequently than.
Yeah, I mean, I think now I get what you're saying. What you're saying is this complicates things, doesn't it? Yeah, sure. It complicates things. It makes life more and more interesting. Okay, do you remember before we had a device called a cache controller, and its job was to manage the traffic between here? Now the cache controller has to manage the traffic between all three of these. If we put in a level 3 cache here, then the cache controller has to manage traffic between all 4 of those. It's a hardware device that manages the moving of data on misses between the levels.
We have to add something about the controller to
No. This controller is independent. No, it's an independent state machine which works faster than the memory. Don't forget, these are memory. Memory's slow. This is transistors made, like a processor, only it's a state machine. It doesn't even fetch code. Controllers have their code buried into their state machine, right? Remember the state graphs that we talked about? Sequential circuits, okay? We've got a state machine in code, not in code, in hardware. The code is the algorithm's in the hardware. Remember CS-224? Sequential circuits, state machines, state diagrams, state tables? Remember all that? That's what a cache controller is. It doesn't fetch code from memory. It doesn't have any memory. Everything is in the transistors of the device. So it's an independent circuit, or actually the cache controller becomes an area on the processor. It becomes an area of transistors on the processor to manage this traffic. So is it slow? No, it's fast. Is it transistors? Yes. Is it complicated? Yes. That's the answer. But the real problem is not that. The real problem is this. So keep your eyes focused here. That's the issues that I want you to stay focused on. Okay. Time's almost up, but we are too. All right, let's look at some issues about multi-level cache. You raised the question. Doesn't it make life complicated? Oh, yeah. Design considerations are very different for level 1 and level 2 cache. What you're trying to do in level 1 cache is not at all what you're trying to do in level 2 cache. The primary cache at the highest level should focus on minimizing the hit time so that we don't slow down the pipeline's clock cycle. So it's got to be fast hit time so that it's skinny and we can have a quick clock cycle. We don't want a shish-go-fat level 1 cache. That means it's going to have to be small. We want short clock cycles, so it's going to have to be small. And as a consequence, the block sizes are going to be small too, because misses means bring in new stuff fast. Secondary caches of this level and maybe the next level, their goal is different. Their goal should be to have a low miss rate. This says have a low hit time. This says have a low miss rate. Why is it not so important to worry about the miss rate from here to here, but to really worry about the miss rate from here to here? Can anybody tell me? Yeah, because the penalty here is the killer, right? This is cache, this is main memory. So therefore, I do not want to miss here. So what does that tell me about my design for this? Big, in order to achieve low miss rates. Look at these miss rates. I didn't work too hard to beat this down. I worked really hard to beat this down. Now I'm less than a percentage here, okay? So that's the key point on that. All right, so therefore, in order to reduce miss rates, what techniques do we know? Large block sizes. What does that do? Spatial and temporal locality. What about higher levels of associativity? Reduce the conflict misses. Yes, sir. These are the techniques that I've just shown for reducing miss rate in a cache. Are these super important here? Yes. Are they super important here? No. What's super important here is this right there. Keep it small, keep it fast, mister. Okay? All right. Now, the miss penalty of a level 1 cache is significantly reduced when you add a level 2 cache. The miss penalty of the level 2 cache is significantly reduced when you stick in a level 3 cache. Okay. That's how we reduce our miss penalties, is by put something faster right below me. Don't make me fall off the cliff. It's kind of like a parachute, you know, or reducing the size of the jump down a little at a time. If you have to jump a long way, you're going to get hurt. You can see there's a long jump from here to 100 or from here to 100. Long jump. Nice to put some caches in the middle. Okay, so for level 2 cache, the hit time is less important than the miss rate. That's the one that we really have to, this is the goal of my level 2 or my lowest cache, is make that dude small so I don't fall off the cliff and pay the big pain. All right, now let's look at two famous processors' caching systems. I'd like you to look at the AMD and the Intel Nehalem and Barcelona. This is the one particularly that our book has a strong focus on throughout the book chapters, but also this is a competitor chip. They're really just two different implementations of the same architecture. And I'd like you to notice they both have level 1 cache, level 2 cache, and level 3 cache. Let's look and see how the two different companies implemented their cache architectures. Level 1 cache is split instruction and data. Just as we expect to feed a pipeline, you feed instructions out of this one and data out of that one. Same thing over here, split. How are we doing? 32 kilobytes for each one per core. If you have multiple core, then you have, but they're pairs and they're 32 kilobytes. AMD decided to go with 64 kilobytes and spin some more transistors for each core. The block size is 64 bytes. Block size is now 64 bytes, which is what? 8 words. 8 words. Block size is big, 8 words in a block. How about associativity? 4-way for the instruction cache, 8-way for the data. This is 2-way set associative. Big difference. How about replacement? Approximately least recently used versus full least recently used. Okay? Well, obviously 2-way LRU is easy with a single bit. Like I told you, in 4 and 8-way multiple bits, it's a lot trickier in hardware, so they compromise on their replacement policy. How about the write policy? Write back with write allocate. Write back with write allocate. No write through here. No write through. Takes too long. We'll write it back later. Level 2 cache. Let's have a look here. How's it organized? Unified. Unified. How big is it? 256 kilobytes or 1/4 of a megabyte? 512 kilobytes or 1/2 a megabyte. AMD seems to prefer bigger caches in order to lower the hit rates. So far, Intel has preferred greater associativity in order to lower the hit rates. Okay? Let's see what else we got here. 64-byte blocks, 64-byte blocks. 8-way set associative with approximately LRU. 16-way set associative with approximately, AMD makes a comeback, says we also know about set associativity, we're going to go big on our level 2 cache. What would you say about this versus this level 2 cache? If we just stop the war right there, what would you say about this one versus this one? I'd say it's bigger and it's got better associativity. It's going to give a lower hit miss rate, isn't it? Higher hit rate, lower miss rate. Clearly, just looking at those two. Okay? Write back, write allocate, write back, write allocate. Same policies here. No write through. Now let's go to level 3 cache. Unified, unified. Whoa, 8 megabytes, only 2 megabytes. How come AMD gave such a small area for their level 3 cache? Yeah, they've been spending their transistors up here. That's one reason. Maybe there's other reasons as well. Maybe they're going to take that savings and spend it somewhere else in pipeline control or cache controller that's a little bit better. Who knows? But anyway, we got a big spend here on Intel's part and a small spend here on AMD's part. Shared by all cores. Notice this is per core. Everybody gets their own level 2 cache. This is all cores now share one common level 3 cache. But it's a biggie. It's also shared by all cores. 16-way set associative. They decided to make the 32-way set associative. Try to, okay, it's not as big, but we're going to get a little bit better performance from big, big associativity. Notice what happened to the associativity. 8 went to 16, 16 went to 32. What's that telling you? What's that telling you? Remember the graphs that I showed you? Look like this. Now what's going on here? 16 to 32, not much change. Not much change, so why are they doing it? A little teeny bit of improvement. What do you want from level 3? What do you want from level 3? What's level 3's goal? Lowest possible miss rate that you can get. Lowest possible miss rate you can get. So, okay, it's not a big deal, but let's go a little farther off to the right here. Squeeze it, baby. Let's get that miss rate down. Even if it's only a 1% improvement, it's something. It's something, okay? All right, finally, write back, write allocate, write back, write allocate. Did anybody see any write through? No, nobody's using write through. Write back saves you the delay of having to write multiple levels. Back to your question, Mr. Kumru. Okay, so that's pretty much what I wanted to say today. We'll see you, what's today, Tuesday? See you on Friday. We'll continue, okay? Have a nice week.